All right. Yes. Final is not accumulative, but it's also accumulative. So the reason I'm saying this is basically we're not going to test you specifically on lines or planes or partial derivatives or the scalar line integral, right? Like the midterm type of questions. But however, all of the questions in the final will actually use the knowledge you learned before the midterm, basically the lines, the planes, the dot product, cross product, the concept of a line integral, and of course partial derivatives, right? So there's no specific dedicated question to the content before the midterm, but there will be the questions that will use those that you learned before the midterm. Yeah. Practice question?
Yeah, like in a worksheet for each content.
Yeah, actually they'll upload it to the Connect already. It's just like the additional exercise I did for the midterm. For each block of content, I think like a double integral, triple integral, vector fields that we're learning now. So you can find them in the folder on the Connect. They are. I'm pretty sure they're all there, but I'll double check. Yeah. Okay. Good? Yeah. So good question, good thinking ahead, because it's coming really fast, right? Yeah. So let's continue on the vector field. We'll look at the vector line integral today. Just a quick review on what vector fields are. You could have a 3D field, you could have a 2D field. The vector field basically comes from a vector function. So when you have a vector function, each component of the function, right, they are functions of variable x, y, z or x, y. Then you essentially get a field of vectors, which give you the so-called vector field. Okay. So what we wanted to do basically from now until the end, pretty much you do everything within a vector field now. The first type of question that we started from previous lectures is called the vector line integral. Okay. So this question here, I started using a very simple question, basically how much force how much work you would do if you apply a force in a certain direction, right? Going a certain distance here. Now, I'm going to basically illustrate this one here with a more general type of question here. So let's say you have, for example, you have a so-called force field. Okay, so this is a vector field. The field basically consists of so many different vectors. Each one of the vectors, let's say, maybe represents, right? So I'm just drawing it arbitrarily. Each one of the vectors represents a certain type of a force, basically pointing to that direction and with a certain magnitude. So what does that mean basically is at this location you have a vector, let's say f1. At this location you have vector f2, right? They point into different direction, give it different lengths. Okay. So if you put an object over here, for example, then that object will feel a force pushing it right to that direction, but that vector, but that force vector over there. Okay? So that's basically what a force field means here. So now, if this whole field, right? If this whole field, I represent the whole field with a vector function f of x, y, z. So that's a vector field. This is a force field basically. Okay. So, and then what we do is we will, let's say, place a certain curve C into this vector field. So this is considered as a trajectory basically. Okay. We place this trajectory in the force field, and then suppose that you're gonna basically place a certain mass over here, okay, starting at this beginning of the curve C. So imagine you place that one mass in the force field. So now that at this location there probably is a force vector pointing, I don't know, to that direction, right? Okay. So that mass will feel this force, and the mass will feel the pushing of the force in that direction. Okay? Yeah. So now you can imagine if the mass is constrained to this trajectory, so the mass will start to move, will be pushed by the force field from one end and then up to this end by this field. That makes sense? Right? So now the question basically here is, how much is the total work done, right, by this force field pushing from one end to the other end of the curve C? Okay, so that's basically the question in here. So total work done, okay, by the force field, okay, going along curve C. So this is the objective we're going to try to find out that here. Okay. How much work does this force field do to push this small mass, okay, across this curve C? So we're going to do this with a very simple basic analogy to the example we did in the previous example here. Okay, yeah. So let's say we take a very small segment ds at here. Okay. So in the previous lecture, remember what we did is you have a small mass at here and pushed to, let's say, by a force and pushed to over here. Okay, that's your d at here. Let's see that. Okay. Right. So this is from previous lecture. We had this one here, and we said that the total number of work done is basically F dot D, right? F dot D is the total number of work done by this F going from here to here, right? Using dot product. Okay? Yeah. So I'm going to use this results that are here apply to this question. Okay? But what I'm going to do is because what we hear is we have actually not a constant vector field. So at a different location on the curve C, that force field at a different location will point into different direction, maybe a different magnitude, right? Yeah. So I'm going to take a very small segment of displacement along the curve C. Why small? Because if it's very small, then I can approximately saying that between this small segment ds, the force vector field is not changing. It's still the same field, right? So that's we can do that approximation in here. So for a small displacement ds here, so now how much work, right, does it do? Okay, how much work does it do to travel this little distance ds at here? So I'm going to use this analogy at here now. So this d here is a ds. Okay, right? This d here is a ds at here. So now I'm going to have to use a little bit strange notation here. So ds here itself is a scalar quantity, right? But it's still displacement concept. So I can still think of this as basically a vector. Okay, so displacement vector here. Okay, yeah. And you have a force vector here dot that small displacement. So for this particular case, maybe at this location here, because this is your force vector fields, right? At that location, you plug in x, y, z, then you get a certain vector field at this location. Because it's so small, so we consider there's no change of force vector field along this ds segment. So I would just use F here dot the ds. So that's the total number of work done by pushing through the mass, right, through this force vector field by only a little bit of ds here, differential displacement ds. Okay. So this is your, for ds, right, this is the amount of work done. Okay. Which is this. Okay. Okay, so let's work from here and then work out the rest of the problem here. F dot the ds. So ds is basically representing the displacement vector from here to here, right? So for any vectors, you have what? You have two quantities. One is direction and the other is magnitude, right? So for this small segment of the vector, so what's the magnitude? ds, right? That's the magnitude of ds. And what would be the direction then for that small segment ds? What direction can we use? What type of vector can we use to represent the direction of the displacement? Tangent, exactly. So I can use the tangent vector to represent its direction. So let's say maybe the tangent vector here is your t hat, right? And that tangent vector, basically the tangent vector from the curve C. Okay? And if you have a curve C parametric equation, and you can easily derive the tangent vector. And it's a unit tangent vector, right? So we're using unit tangent vector here. Okay? Yeah, so t hat ds. So that's it. So you see the dw equal to this. Okay, so this is basically how much work you do for very small differential ds. And naturally, if you see, then what's the total work done then, right? So total work done, you have this one here. Total work done, basically you integrate this dw, right? You integrate this dw along this curve C, and you get the total work, right? That's the integration concept. So basically we're integrating this side here, so F dot t has and ds here. Okay, so this is basically the total work done by this force field, okay, through this curve C. Is that good? Yeah. So I want you to actually take a second look at this. This result set here. What's this in the between here? So it's what? F dot t hat, isn't it, right? Now, if you recall, what we in the first lecture, or maybe the second lecture, what's the meaning when you have a vector dot a unit vector? Projection, right? So this is a projection of this force in the direction of t hat, and t hat is the direction basically moving along this curve C, right? So ultimately, you can think of this essentially. This is the projection of force at that location into the t hat direction. Then dot the ds, give you the work. You add up all the total small work, you get the total work. Okay? Yeah, that's basically the idea here, right? Yeah. And the other way of thinking is this. So this one here, this is basically the projection of F in t hat direction. And the other way of thinking is this is, okay, so at one location, you project F into the t hat location. At the second location, you do the same thing. And then what happens next is you're integrating over the curve C. You're adding up, right? You're adding up all of these projections in the t hat direction, right? The projection F in the t hat direction. So often in time, okay, and this integral right here, okay, is called circulation. Basically, the circulation along the curve C. Okay. So I'll give you a slightly different example here. Let's say, now I will shift your mind here. Instead of force field, right? Think about maybe it's a river, okay, a velocity field. Okay, so basically here you have a velocity field. Okay, And then maybe you have a certain curve, a boundary. Okay, so whatever shape that you place inside, okay, this velocity field. Okay. So if I apply the same formula, okay, change the force field to the vector, to the velocity field, okay, to the velocity field, and this is your curve C. Okay, it's a curve C here. So now you can imagine what's the meaning now. This is basically you're calculating the circulation of this velocity field along this curve C here, which could be a profile, right? Could be a profile. So you see that this so-called vector line integral here. This is basically the vector line integral. This vector line integral here, you can literally give it a different type of meanings at it here, right? Yeah. I approached it using a force field and total work done, but you could always apply it to a completely different principles, okay, or meanings. Okay. So let's continue from here, right? Ultimately, we want to evaluate this vector line integral. So how do we evaluate this one here, right? So let me continue from here. Okay. So continuing from here. Let's see, how do we evaluate this one here? Going back to this formula here, first of all, ds, right? Let's look at what ds is. ds is basically what? It's the small line segment, right, or curve segment along the curve C. Have you learned this before the midterm? Right? This is basically the so-called the little arc length, that type of question, right? So the ds you actually learned before, and the formula for ds is this, right? That's your small arc length, okay, or curve length, okay, along the C here. That's your ds. And then your t hat, right? T hat is the unit tangent vector to the parametric equation. So how do we get the t hat? We take the derivative of this parametric equation and then divided by its length, we get the t hat. Okay? Yeah. So this is basically t hat and ds here. Now for ds, okay, I can simplify this just slightly at here, okay, just slightly. When you have a vector, dr over dt is a vector. So when the vector dot itself, then you get basically the square of the norm. So for this square root here, you essentially get, it's the length, right? It's the length of the dr over dt, and then times dt. Okay. Yeah. So now I'm going to put these two together, right? Put these two things together here and put it into this vector line integral formula. So if I put into this vector line integral formula, so let's see what do we have here. Okay, so let me write again at the bottom here. So f, okay, dot. So the t hat is dr over dt, and then over dr over dt and here. So that's your t hat. ds is this guy here. Okay. So you look at this, you look at the results that here, you cancel this, basically you cancel these two terms, and what we end up with and dt, okay, like this. Does that make sense? Yeah. So this is basically the evaluation of the integral. Now up to this here, we are able to actually evaluate this line integral now. Okay? Yeah. Because why? The question probably will give you the parametric equation for the curve C, so you can take the derivative. And the question will give you this parametric equation F, So what do we do with f then, right? So the f here is this f of x, y, z. However, you are integrating along which curve? Along the curve C. So f itself, like this, like draw f itself is a vector field everywhere, but you are doing things only along the curve C. So essentially the x, y, z for this vector function will be restricted to the values on the curve C here. So your f here, you need to replace the f with the parametric equations x of t, y of t, and z of t. Okay, so that's what you do with this f here. So once you do that, then everything is right. Everything's done. Then you can do the rest of the operation here. So I'll give you an example. You'll see it's actually quite straightforward. Okay. Yeah. Alternatively, for this formula, you might argue is, okay, so I actually can cancel this dt here. So yes, so you can sometimes you can write this formula just like this. So f dot dr, okay, dot dr. But I prefer this one here because ultimately, when you calculate dr, you actually will still have the dt ultimately showing up. Okay, yeah. So you might as well just calculate this derivative here. Okay, and the range of the t depends on the parametric equation, right? Okay. Okay, so let's take a look at an example here. Okay. Very simple example. Then just to get some idea of how to do this type of question. So I have a vector field. It's a 3D field for sure. And then we have the curve C given by Ti hat. So question gives you everything. So you have a curve C, t squared, t cubed. The t goes from 0 to 2. Okay. Now we want to calculate basically the line integral, okay, along this curve C here. Okay. Okay, so instead of directly jumping into this one here, so I'm going to write things just slightly in components first, and then put them together. Right. First of all, what do you do with this vector function f here? So remember this one here. You replace your x, y, z, okay, with x of t, y of t, and z of t, okay, and that's from the parametric equation, right? Okay, so if you do the replacement here, let's take a look at it. What do we get? You replace the y with t squared, replace the z with t cubed. So the first term is t squared t cubed. Second term, replace the x with t, replace the z with t cubed. So t cubed. Last one, replace the x with t, replace the y with t squared. That's the vector function f, or vector field at the different locations along the curve C. Okay, so altogether you get a t5, t4 and t cubed. So, and then you deal with dr over dt. So dr over dt, you get 1, 2t, 3t squared. Finally, you put things together. So put things together here. So integration. The range of the t goes from 0 to 2, so it's 0 to 2. It's a dot product between t5, t4, t cubed dot 1, 2t, 3t squared, then dt. That's a simple dot product. So t5 times 1 plus t4 times 2t, so 2t5, t cubed times 3t squared, so 3t5 to the power 5, and dt. And altogether 6t to the power 5, and you can integrate that easily, so you get 64. Okay. So that's the results of this simple line integral right here, right? And you can interpret it differently. You can see this is okay. So this is the total number of work done by this force field F along the curve C, which gives us a 64 Newton meter or something like that, right? Okay. Any questions? So as you can see, for this kind of question, right, it's very similar to the scalar line integral, except we're dealing with it's a vector dot product here, right? But the kind of concept of substitution for x of ty of tz of t, it's a similar type of concept, right? Okay. Okay. For the same, let me rewrite this. Okay. Maybe just rewrite this one here. For the same vector line integral formula, okay, often in time you will see a different actually formulas, alternative for this formula here. So here's another alternative. So if I shorten this vector field F, okay, which is the three components M and P, and then if I have this derivative of the dr of this parametric equation, which is dx, dy, and dz. Okay. So now if I substitute these two into this formula, and we would get basically M and P dot dx, dy, dz, and then you get M dx n dy plus p dz. So this is basically another possible starting point, okay, for this vector line integral. Okay. So now you see you have a really different type of approach to calculate the vector line integral now, right? So at least three different types. Okay, three different types. They're all the same, but depends on how comfortable with the symbols that in each one of the formula here. I'll show you an example using this one and here, right? Yeah. Honestly speaking, I think this is the one could cause a little bit misunderstanding sometimes among yourself for this formula here. Because this is a little sometimes confusing, because you look at this one here, oh, this is a dx, dy, dz. It very much looks like what? You're integrating with respect to the x variable, y variable, z variable, isn't it, right? Yeah. But it's actually not. So the dx here, for example, this is x, this for this particular curve, x is t, y is t squared, z is t cubed, right? So the dx here, it's really just dx of t. If x of t is, let's say, it's t squared, then what you really have now is what? It's 2t dt. Okay, so that's really what's behind the dx, dy, dz. Okay, yeah, it's not just the dx, dy, dz. It's actually there's another level of derivatives involved here, right? Yeah. So let me show you an example here, right? Let me show you an example here. Okay. So we'll take a look at an example here. Right click doesn't work. Okay, so this is a vector field, and this is the curve C. And we want to calculate this vector line integral. I think I illustrated this vector field in previous lecture, so it's more of like a spinning field at here, right? The curve C, this is all planar case. If you plot the curve C out, it's basically y equal to x squared. Okay, that's part of this, and then the t goes from 0 to 2, okay, like that. So it basically goes up like this. Okay, to calculate this vector line integral here, you can try. Essentially, you can start from any one of these formula here, right? Yeah. You can start from here or here or here. It really doesn't matter. Okay. So for this one here, I'll just illustrate how you can go from here. Now this formula is for 3D. You have a dz and p here, but this is a planar case. So honestly, you don't have that. Basically, you don't have that dz component. Okay. You just have this m and n components at here. So you can basically see what is m, what is n in here. So this is your vector fields, right? So this is your m, this is your n, and this is your x of t, and this is your y of t. M supposed to be a function x, y, n supposed to be a function x, y, and of course, I mean, in this case here is just a simple negative y and x for both of the functions, right? Yeah, so it's not too bad. Okay, so I'll look at let's look at this from here. How do I proceed from here? Okay, so we will basically I'll write maybe a few just scrap here. You will replace the m with x of t, y of t, and you replace the n also with x of t, y of t. So let's take a look at it. And here's my m and here. This m is just negative y. So I will replace the y with what? With y of t. So my m end up with just a negative t squared. And the n, you replace the x with t, so just end up with a t for the n component at here. And dx, okay, so dx, it's ultimately just the dx of t. It's dx of t is a t, so just a dt. dy is basically dy of t. It's a dt squared, which is 2t dt. Okay, that makes sense? Yeah. So now you put all of these things together into the formula here. Okay. So I'll just equal sign come over here. Okay. Yeah. Okay. So what are we integrating now? M is negative t squared. Dx is dt. And dy is also, there's also dt in up here, so that'll be common factor here. The n is t, so t and dt, and t goes from 0 to 2. Okay. Sorry, I missed it here. No, so let's go back. Let's go back here. What's m? Let's write it one more step. M is what? Negative t squared, right? M is negative t squared. What's dt dx? Dx is dt. What's n here? N is a t. What's dy here? It's 2t dt. Okay? Yeah. So altogether, you get negative t squared plus 2t squared dt. So cancel 1t squared, become t squared, and the end up is 8 over 3. Okay, so that's a different. If you use a different formula, right? It's the same. I mean, if you're starting from here, dr over dtf here, okay, and you should get the same answer like you starting from here. Okay, so either way is fine. Depends on how comfortable you are, whichever formula that you wanted to use. Okay, and that will be okay. Any questions? So I think it's should be a pretty straightforward type of questions. Okay. Yeah. So before we move on, let me give you another simple example. Okay, it's a simple example. Basically, I'm not going to ask you to calculate. Just to look at example, you actually will be able to tell the answer. But let's look at example first. Okay. Yeah. Here's a vector field xy, and curve C is x squared plus y squared equal to a squared counterclockwise. Okay, counterclockwise. Well, so now you have the vector field, and you have the curve C, and we want to calculate this vector line integral. So you can proceed calculating this line integral by a typical process. But in this case here, if you really wanted to do, you actually would have to find the parametric equation for the curve C, right? So for curve C, you're going to have to find it. Okay, so it's a cosine t, for example, right? And a sine t, okay? And t go from 0 to 2 pi. Okay, so that's the parametric equation for a circle. So then you can substitute this one into this line integral formula, and then step by step, and you'll be able to calculate the line integral. Huh? Yeah. Now, but I want you to take a second look at this one here. You actually will be able to draw a conclusion if you're actually able to sketch this whole thing out. Okay. So first of all, let's sketch the circle. So this is the circle right here. Okay, so this is your curve C, right? Goes from here to here. And second of all, you should sketch this. You should be able to sketch this vector field. So this vector field is the x, y, and I think I actually illustrated this field in the previous lecture. So if I pick a point on the curve C, and I draw the vector field out, and guess what? It's just a vector field F, right? Pointing out of this origin, okay? Because it's x, y, right? For any positions, you can point it out, okay? Like this. For any positions. Okay. So when you see this F and the curve C, now if you actually remember, what's the connection, what's the relationship between the vector and the curve C? Perpendicular, right? Perpendicular. So for the vector line integral, if I go backwards, actually I used my most original formula, which is from where? From f dot t hat ds. right? F dot t hat ds. And what's t hat? T hat is at this location. T hat is this. At this location, t hat is this. What's that? T hat is basically the unit tangent vector to the curve C. Okay, to the curve C. So now you can literally see now what's the connection, what's the relationship between the vector f and the t hat. They are perpendicular, 90 degree. So now you have this f dot t hat. This should equal to 0. So the whole line integral here should equal to what? 0. Okay? Yeah. Because there's no component, projected component of this f in the direction of t hat. Then the total integral will, of course, will be 0. Right? Yeah. So that gives you another perspective doing line integral sometimes. You know, it could be much easier. Right? Yeah. And of course, this is just for this vector field, right? If you change the vector field to something else, and then it's not going to be 0 anymore, right? Yeah. Well, maybe it's a 0, but it's not going to be as straightforward like this anymore. Okay. So, any questions on the vector line? Yes.
Where did you get a cos theta?
Oh, that's the parametric equation for the curve C.
For x squared plus y squared?
For yeah. So if I substitute this here. Substitute this here, what do you get? You get a square, right? That's the parameterization of the curve C, isn't it? Yeah, yeah. And you can use a different 2t or 3t, right? Yeah. Okay, so let's continue at it here now. Okay, and we're gonna start a new topic called conservative field. And I'll cover what the conservative field means here. Okay. Now there is a very special kind of a vector field. Okay, so there's a very special kind of vector field. This special vector kind of field is so-called the gradient vector field. Okay, the gradient vector field. So I'm not actually talking about conservative fields yet, but gradient vector field basically is the conservative field. So what is a gradient vector field? Basically, if you have scalar function f, then you take the gradient of that function, then you get a gradient vector, right? And that vector is basically, it's the so-called gradient vector field, gradient vector function, or whatever, right? So, for example, if your function f is a function of 2 variables, then you get your gradient field will be basically a function 2 variables. It's a 2D fields, right? It's 2D fields. So what was that? It's partial f, partial x, partial f, partial y. Okay, so it results in a 2D field. If you're given as a 3D function, then you would end up with a 3D field. Okay, yeah. So that type of concept here. Okay. This gradient vector field is a very special field. So this one here, where I can see it early, this is basically a so-called conservative field. Okay, and then I'll see more details. What exactly does conservative field means? As a matter of fact, you probably already are able to conclude something in your mind now. What does conservative field means? Total work done is 0. Yeah, as you're going along the circle, right? That's conservative field. Okay? Yeah. So a few comments in here. So this function f, okay, is called potential function. Okay, this one here is called potential function for this field F at here. Okay. In your first year or in your high school, we actually have come into contact with two very common conservative field or gradient vector field here. So if you recall that we have basically a gravitational potential. Okay, I'll show you. Okay, we can have a gravitational potential, and then if you take the gradient of the gravitational potential function, it'll yield a gravitational field. Okay, you yield gravitational field. For example, what's the gravitational potential? Gravitational potential function is V equal to negative Gm over R. Okay, that's the gravitational potential function. G is the gravitational constant, M is the mass of the Earth, and R is the distance basically from the center of the Earth to wherever, okay, location. And if you take the gradient, okay, if you take the gradient of this gravitational field, okay, yeah, and actually add a negative here, you'll get this so-called gravitational field. So this gravitational field is equal to negative G and M over R square and R hat, okay, like this. So that's a gravitational field. Okay. So we're all living in a gravitational field, right? Yeah. Similarly, you could also have, okay, like this. You can have a electric potential. Okay, and if you take the gradient of the electric potential, and you will get electrical field. Okay, you'll get electrical field. So for example, if you have a point charge, okay, if you have a point charge Q, okay, so positive, let's say point charge or negative, doesn't matter. So you can this point charge will create an electrical field, but the potential field for this one here is for this point charge is, okay, is Q over 4 pi epsilon naught and times R. So this epsilon naught is so-called electric constant. Okay, electric constant here. Now, if you take this gradient of this function right here, this potential function, okay, so all of this I will skip the calculation, but you can check out my lecture notes. You'll be able to see that. So you will be able to get this so-called electrical field E, which is Q over 4 pi epsilon, okay, 1 over R square and R hat. Okay, R hat. So that's an example, basically what type of a field in reality we're living in, right? But overall, this one here, okay, this is a pure mathematical concept. So the F here doesn't have to be electrical potential, doesn't have to be gravitational potential. It's just mathematical concept called potential function. And you take the gradient of the potential function, then you get a gradient vector field, and the gradient vector field here is a conservative field. And I'll show you. We'll show you what conservative field actually means. Okay, using this vector line integral concept. Okay, yeah. Yeah. So bottom line is, you apply the gradient operation to any scalar function, then you get a conservative field, basically. Okay, yeah. So then what's so special about conservative field then, right? What's so special about conservative field? Okay, it's basically we can make use of a very important theorem, which I'll write down shortly, when we evaluate this vector line integral inside this conservative field. So I'll present you a theorem at here. This is actually one of the most theorem, okay, in calculus. So it's called fundamental theorem of a calculus. Now up to this here, it should actually remind you in the first year. What's the fundamental theorem of calculus? No? It's all gone? It's something about the limits, eh? Yeah. And what is it equal to? Right? Yeah. That's a fundamental theorem of calculus, right? Okay, but this is not what I'm going to cover here. It's a fundamental theorem of calculus for line integral. Okay, for line integral, or vector line integral, more precisely. Okay. So I'm not going to cross this out. I'll just leave it on this one here, but make sure you understand this is not part of this. This is not part of this theorem right here. Okay, this is a part of your previous theorem. I might as well just erase this here. Okay, just not confusing here. Okay, given a curve C. Okay, given a curve C. Okay, runs from initial point P naught to finish point P1. Okay, it's like this. Here's P naught, here's P1. Okay, this is the curve C. Alright? Yeah. Or instead we can see, okay, so T, okay, instead we can see this is a curve C, and then the T value goes from, let's say, A to B. Okay, so this is T equal to A, and this is T equal to B. Okay, so here's a curve C. Okay. And now imagine, okay, you have a field around this curve C. Okay, you have a field around the curve C here. It's spread it in the 3D space. Okay. And this field F at here, okay? So this field F it's a very special field. It's the gradient field, or it's a conservative field. Okay. Then if you're asked to evaluate this line integral inside this conservative field from P naught to P1, or along this C at here. Okay. Yeah. So technically speaking, you can literally replace the F with del F, because that's where this F is from, right? Okay. You can replace that with this. But the good part is you don't need to calculate this line integral as what we did previously, okay, in the first hour or something. You can use this fundamental theorem of calculus for this. How do you do? This is basically what happens here. Now, that's how you can calculate vector line integral inside this conservative field. What does this mean? Basically, it means this vector line integral equal to what? Equal to the potential function, the value of the potential function at the finish point minus the value of the potential function at the initial point. P1, P naught here basically representing the coordinates, right? You're going to replace the coordinates P naught and P1 for the function f and here. Okay, that's called fundamental theorem of a calculus for line integral. Yeah. Well, it's actually quite straightforward, isn't it? Right? Because if you think of in terms of a gravitational field or any work done in a gravitational field, and guess what? When you go from P0 to P1, does the root matters? No, right? All it matters what is the ending point and the finishing point. Okay, so that's basically what matters here, right? Yeah. There's a very brief proof for this theorem at here. So let's just quickly go through the proof here. These are quite important. I think it's not many lines of proof, so let's go through this. Okay. Okay, so C is, let's see, any arbitrary curve C. Okay. So given the C is arbitrary curve C, and now I'm going. What we're required to do now is to do this vector line integral. Okay, so to do this vector line integral, right? Okay, so basically you're integrating for the t goes from a to b, and this one here I'll use the other formula, basically just dr over dt times dt. It's the same thing, right? Okay. So now I will expand the gradient at here. So the expanding this is fx, fy, fz, and then dot dx, so this is a dx over dt, right? Dx over dt, dy over dt, dz over dt, and times dt. Okay? Yeah. And expand this dot product. You get fx dx over dt plus fy dy over dt and fz dz over dt and dt. Okay? Dt. Okay. So now look at if I multiply the dt into this bracket, what do I get? Fx dx plus fy dy plus fz dz, right? Dz. Okay. And this is basically what? If you recall that in the previous lectures, when we learned the multivariable calculus, the partial derivatives, this whole thing is basically so-called what? Total differential, right? The total differential. So you're integrating a to b df. So integrating d anything give you back that anything. So it'll give you back this function f here. So it'll give you back the function f, and that represents f of xt, y of t, and z of t. And t goes from a to b. So when you plug in a t equal to b into this function here, and this is basically means the value at p1 minus the value at the initial point p0, right? Okay. So that's the simple proof for this conservative field here. For the function of fundamental theorem of calculus for line integrals. Okay. Okay. So let's take a look example. Okay. Application of this theorem, okay, through an example right here. So for this example, we're going to deal with Okay, so I'll give you a vector field and also a curve C. So here's the vector field F at here, which is sketched out by the red line in here. Okay, so you have a it's not a spinning field, but you know, it's not a regular field at all, right? So it's F equal to yx at here, and the C equal to 3 segments, C1 plus C2 plus C3, which is illustrated right here, C1, C2, C3, and all together it's basically like a piece of pizza. Okay, yeah, and a vector field is like the pepperonis on it, right? So, and we're trying to integrate this vector field over the curve C. Okay. Good. So, particularly the C2 at here, okay, is a part of the circle, basically. Okay. And the angle at here is pi over 4, so 45 degree. So you probably can't see that clear, but this is the origin, basically, right? You can see this is origin. So A point is right at origin, 0, 0. Okay. And the B is right here, so that's basically part of circle x plus y squared equal to 1, so that's the circle here. Okay. And then D is at the angle pi over 4. Right. Alright, so that's the question right here. Okay, this question. Now, if the question is just like that, okay, then what are you going to do with this line integral? So I guess you probably actually, a very natural approach is, okay, so let's go ahead and then, because C has C1, C2, C plus, so I'm going to basically do 3 different line integrals, right? So do C1 first, C2 and C3, and then add them together, then we get a total line integral. Okay, yeah. So that's actually what next week tutorial will show you how to do this if you do this each one of the line segments. But of course, in order to do this, then you have to get the parametric equation for each one of the segments of these curves, right? So for example, maybe C1, okay, so from A to B, y is always 0, and so if this C1, so y is always 0, x is changes, so maybe I can let x equal to t, and then y equal to 0, so that's your parametric equation, and t goes from 0 to 1, right? So that's how you get the parametric for C1, and then C2, and you can literally use that circle, so that radius is 1, so basically cosine t and then sine t. Okay, so t goes from, let's say, 0 to pi over 4, right? Okay, and for the C2, that's a part of the line segments that are here. Okay, so go from d to 0. Actually, you should think about what C3 is, right? So, but that's parametric equation. I'm going to write it down. So anyway, so you can try with C3, but that's not the approach I'm going to illustrate it here. And this is the approach that you do when you actually don't know what type of this field, this F is, because I didn't tell you what this is. A vector field. Is there any special field, right? It didn't tell you, right? And you actually cannot identify right away just by looking at this vector function here. So for now, I will tell you is this vector field, okay, it's actually a greeting field if you try this out. If you let this small scalar function equal to xy, and you take the greetings of this one here, and look at what you get. So partial f over partial x, y, right? Partial f, partial y, x. That's the field you get here, right? Yeah. So this is the conclusion I gave it to you, right? By looking at this one here, then what does that mean? Basically means this is not a random field. This is actually a special field because it's a gradient field. Or what do we call that? This is a conservative field. Okay? It's a conservative field. If it's a conservative field, and guess what does this equal to? 0, right? You should get a 0. But I still don't quite believe that, so let's try it. So I'm going to use the fundamental theorem to try this out here. So I'm going to use, let's say, for C1, okay? Before we do this, let's first of all, let's find the coordinates for A, B, D at here, okay? So what's the coordinate A? It's 0, 0. That's pretty simple. Coordinate B is 0, 1. That's 1, 0. Okay. It's 1. What's the coordinate B? No. Yeah, coordinate B is 1. X equal to 1. Yeah, x to 1, y equal to 0, right? Yeah. And what about the coordinates of D at here? What's the coordinates of D? Here's pi over 4, so the coordinates of D is cosine 45 and sine 45, right? Everybody sleeping? Yeah? Yeah? Yeah. So cosine 45 equal to root 2 over 2, root 2 over 2, right? Okay. That's your D. Okay. So now I will apply the fundamental theorem of calculus now. Okay. So if C1, according to the fundamental theorem of calculus, I don't need to calculate this line integral. All I need to do is use the end value for the potential function minus the value of the potential function at the beginning point. So basically for the C1, it starts at A, end at B, and here is my potential function x, y. So B is x is 1, y is 0, 1 times 0 is 0. And f of A is 0 times 0 is 0, 0. So this whole, the first segment of line integral is 0. The second segment of line integral is f of D minus f of B. Okay. So what's f of D? F of D is you replace x and y with root 2 or root 2 over 2. So basically you get root 2 over 2 times root 2 over 2 minus b. B is 0, and I end up with a 1/2. Okay. And finally, for the line integral over C3, it's f of A minus f of D, which is 0 minus 1/2, so negative 1/2. Okay. Yeah. So you add all three segments together, so obviously it's 0. Okay. Yeah. It's a little redundant, but it just shows you can use the fundamental theorem calculus to actually basically prove that within a conservative field, the line integral over a closed curve is 0. Right? So that's actually one of the comments here. When you have a closed curve, so I use this one here. So dr equal to 0 here. Okay? For conservative field. So if you see an integral with a circle at here, basically means that C at here is actually a closed curve. Right? Closed curve here. Any questions? Okay. And I think you should have a question at this stage. Actually, one of the students from the other section asked me this question here because the lecture finished here. If the lecture finished here, then there should be a question, which is what? How do you know this vector field is actually come from here, right? How do I know? How do you even know that this is a conserved field, first of all? Or if it is conserved field, and how do you even know that you can take a gradient of this function? Okay, you can gradient this function in here to give you this vector field, right? So, because by looking at this vector field here, we're not going to be able directly just to draw a conclusion. Okay, so this is conservative. It's actually taking the gradient from here. So it's not that easy to observe, right? Especially if you have a much complicated basically here. So that's actually the next topic. I'm not sure if I have the time, but I have a few other things just to write it down here. Basically, there's a question in here to ask is, so how do we know that this f is conservative? So this is the first question we need to answer. Okay. The second question we need to answer is, if f is conservative, okay, if this is a conservative field, then what is its potential function? Okay. So basically means, how do I find this f at here, right? How do I find this f at here? So that's the two questions that we need to answer, okay? Naturally from here. How do we determine it's a conserved field? If we determine it's a conserved field, how do we find its potential function f, so that you take the gradient of that function f, then you get back to this field as vector fields at here, right? Okay. So this is basically the question we're going to answer it here. But before we answer this question, I just need to summarize a little bit, and then we can move on to these two questions over here. Okay. So I'm going to provide a summary at here. Okay. This summary here, basically, I call it 4 equivalent properties. Okay. 4 equivalent properties. What are the 4 equivalent? So I'll just write down 4 statements. They are basically equivalent to each other. Yes?
If the force and the motion are perpendicular, does that mean it's always conservative?
Force and the motion.
Yeah.
No. You have to be careful at it here. There are 2 different concepts here. So see here, right? I think so here, for example, this equal to 0, right? So like the example showed you, the C is a circle, F is perpendicular to the circle, right? And then you end up with the integral equal to 0. But that doesn't necessarily mean that this equal to 0 doesn't necessarily mean that this one here is a conservative field. Is that clear?
But doesn't the pathing come to the same place, so it ends up?
Yeah. So this equal to 0 doesn't mean this is a conservative, okay? But if it's a conservative, then if I have a closed curve, then it's going to be absolute 0. Okay? If it's not a closed curve, then you can use that fundamental theorem calculus there. Okay? Yeah. Actually, this has something to do with the 4 equivalence statement I'm writing down in here. So let me write it down here. Maybe that'll answer part of your question too. So, first of all, f is conservative. Okay? So this is the one statement at here. So f is conservative basically means you integrate this f over any closed curve C. it'll be 0. That's the first statement. And second statement, if curve C is not a closed, okay, it's not closed, then you integrate over this curve C, but this integral here is path independent. Okay, it's path independent. It only depends on what? Only depends on the finishing point and the ending point, the starting point. Okay. Yeah.
All of them are just conservative.
Pardon me?
All of them are just conservative.
All of them? Oh, what do you mean?
No, for F.
Yeah.
Independent F. Is that for any case or is that if it's conservative?
Only for conservative. Yeah. Only for conservative. Yeah. If it is not conservative, if it's arbitrary, then this property doesn't satisfy. Yeah. F is a grading field. So if the vector field comes from the gradient operation of a scalar function, then it's naturally a conservative field. Okay? It's naturally a conservative field. And the fourth statement here is more or less to do with the writing. So let's say your F is M in P. Okay? Yeah. Then this F, okay, equal to F will yield an expression, okay, like this. So a little bit of derivation here. So M and P equal to Fxi hat, Fyj hat, Fz k hat. Okay, right? That will yield this relationship. Okay, because you're taking the gradient at the end of this vector field. Okay. Okay, so now if you're going to integrate this vector field, okay, over hang on a second here, let me see, how do I, yeah, okay, so then what we can do is, so you see, basically you have an M equal to Fx, and N equal to Fy, and P equal to Fz, right? Okay? Yeah. It's a little bit confusing here. Right. Okay. So, and now, if I'm going to integrate over the curve C, and this is equivalent to C integrate over curve C, right? Over the curve C here. Okay, so this one a little bit longer writing here. So I'm gonna substitute this M N P at here. Okay, I replace the dr with dx, dy, dz, and then this one here replace with fx, fy, fz, and then dx, dy, dz similarly. So when you do the line integral here, you integrate over the f vector field or this potential function del f. It's the same thing, right? So then this one here is m dx plus n dy plus p dz, and here is fx dx plus fy dy and plus fz dz. So I got basically an equivalent expression here. At here, okay? So now you see, basically what does it mean is your m dx plus n dy plus p dz equal to this fx dx, fy dy plus fz dz. Okay. And this fx dx, fy dy, fz dz is the total differential, right? It's the total differential right here. So basically you get m dx plus n dy plus p dz equal to this. Okay, so this is your number 4 over here. Okay, your number 4. So your m times dx, n times dy, p times dz equal to a d some scalar function. Okay, this scalar function is your potential function. This is actually called exact differential. Okay, an exact differential over here. Okay, yeah. As a matter of fact, you're learning 246. So for differential equation, this is one type of differential equation. It's called exact differential equation. If you can write it into an exact differential equation, you actually can solve that differential equation immediately by finding this f, which is the solution in here. Okay. Yeah. So that's the 4 equivalent statements. Okay? Yeah. Any questions? Okay, good. Yeah.
I had a question. When we did the circle, I don't think I drew it, but basically all the forces cancel out, right? You had the circle and then we had
No, the
tangent.
forces cancel out.
Yeah, sorry, the force. Well, but the force vectors they would always have an opposite.
Yeah, it's basically means because we're integrating. Well, see that line integral here. The line integral here is you're integrating the project.